Hello everyone. Today we will discuss about the energy stored in an inductor. So for power we know the formula is VI. So we can replace V by E. This can be written like this. Power can be written as rate of doing work. So this can be written dW by dt. And we know that the magnitude of the induced EMF is L di by dt. So where this is the of induced EMF, magnitude of induced EMF. So we can mark this as equation 1, this as equation 2 from 2 in 1. We can write dW by dt is equal to L di by dt into I. This can be cancelled because both the sides we are checking the rate of change with time. So this can be cancelled. This is dW is equal to L I di, right? So the total work done in establishing the current in the circuit due to induced EMF which opposes it is stored as magnetic potential energy in an inductor. Right? So we can mark this as equation 3 for total work, integrating for total work. So we are integrating it. dW is equal to integral Li di. What will be the limits? The limits will be, this will be 0 to W, this will be 0 to I, and this is stored as magnetic potential energy. So I am writing the suffix UB. This is actually magnetic potential right. So dW integral is W. We put the limit 0 to W, this will remain W only. L can be taken outside the integral sign because L depends on the geometry of the conductor and medium which is there in the coil, and this can be written I di. So right side integration of I is I square upon 2. Current is established from 0 to I, and this can be upper limit minus lower limit. So left side we have W which is stored as potential energy. So this is written as UB is equal to L upon 2 I square minus 0 square. This step I have written just to explain. You could have skipped the step and written directly without showing this particular step of putting the limits. So this is magnetic potential energy which is half L I square. Now we'll calculate the magnetic potential energy density. Now what is potential energy density? The potential energy density is energy per unit volume. So this is energy that means this upon volume, right? So if we consider a solenoid whose length is this and area of cross section is this, what will be the volume? It's like cylinder, so this can be written as A into L. What is the formula for magnetic potential energy? This is half L I square. What is the formula for the self inductance of solenoid? L is equal to mu naught n square A L, where small n is number of turns per unit length, right? So this can be written n upon L, right? And what is the formula for the magnetic field due to solenoid? This is mu naught into small n into I. So from here current can be written as B upon mu naught n. Let's mark these equations. This one as 1, right? This one as 2 and this one as 3. So from 2 and 3 in 1. So put 2 and 3 in 1, you will get magnetic potential energy in this form. Half L is how much? Mu naught n square A L, and I is how much? B upon mu naught small n, this is square, right? We know that magnetic energy density is UB upon AL, so we can write UB upon AL. So I have shifted this part in its denominator, so this will come out to be half mu naught n square into B square upon mu naught square into n square. So this gives, this n square will be cancelled, n square will be cancelled, single mu naught will be cancelled. So this gives me B square upon 2 mu naught. So you can write down finally that magnetic potential energy density, or simply energy density, that is UB upon volume. Why? Because this is AL is volume. So this is the formula for the magnetic potential energy density. Why? Because here A into L is equal to volume. So that's all about the energy stored in an inductor and the energy density. Thank you and have a nice day.